Hello everybody, in this lecture we will be solving 1992 IMO problem number 5. Here is a view of this problem. Let S be a finite set of points in the three-dimensional space. Let S sub x, S sub y, and S sub z be the sets consisting of the orthogonal projections of the points of S onto the YZ plane, ZX plane, and XY plane respectively, and we would like to prove that S square, the number of elements square, is less than or equal to S sub x times S sub y times S sub z, where the absolute value represents the number of elements in those sets respectively. And there's also a note about the definition of an orthogonal projection of a point onto a plane, which is simply the foot of the perpendicular from that point to that plane. Okay, so let's first draw our three-dimensional space with the x, y, and z axes. And so you have all these points scattered on the 3D, and what I will do is, let's first make the following assumption. Let's assume that all the z coordinates accepted by these points are the following. So all these all these points have only the following z coordinates. So obviously some of them might be negative. So let's say that this is z1 and up to z sub n, and this is a typical z sub I. So the horizontal plane containing z sub I, let's assume that's that plane. So you have a bunch of points on this plane, and these points, let's call this layer as L sub I, and the number of points on this layer as a result will be the absolute value of L sub I. L sub I is the number of points on layer L sub I. Okay. Next, what I will do is I will count. Obviously, when you count these points, so on the horizontal and on the vertical, you will see that some of these points are coinciding with respect to the x coordinate. So if you gather together all the x coordinates of these points, let's say that there are a sub I different x coordinates, like this one, and then these two are on the same one, maybe these two are on the same, these three are on the same, these three, this one is by itself, and so on. So do you see that all these points accept a sub I different x coordinates? In a similar way, one can count how many different b values these points would take. Like these points are all the same b values, this one is the same, like that, these three are on the same. Okay, so let's assume that, let's put the L sub I on this side, I guess, L sub I. So on layer I, L sub I, the y coordinates accept b sub I different values. As a result, we have a grid. Not all the lattice points on this grid, not all the points of intersection on this grid are elements of the set S. As a result, L sub I should be less than or equal to a sub I, b sub I. So that's our first observation. Another observation is that all these layers, we have in total n layers, right? The number of points in layer 1, the number of points in layer 2, and so on. All the layers are classified with respect to their z coordinates, and so this whole thing should give you all the count in all the sets. And in addition, the count of the x coordinates in each layer, if you add them up, we will get S sub y, right? So S sub y is simply the count of all the x coordinates, the count of all the x coordinates, right, in the in the given plane. And in a similar way, S sub x would simply be equal to b sub 1 plus b sub n. Okay, so now we can also take an orthogonal projection of all the points on layer L sub I onto the xy plane, and as a result we would see that L sub I would be less than or equal to S sub Z as a result. So that's result 4. Is that clear? Because, well, the two can be equal if on the layers, for instance, if you have only a single layer, right? Or if you have multiple layers, but the points on the layers or their orthogonal projections onto the xy plane, they coincide, basically. Okay, so finally we can go ahead and multiply 1 and 4. So let me write that down. Multiply 1 and 4 to get that L sub I squared is less than or equal to A sub I, B sub I, S sub Z. So the product of these sets, and now connect. I will start with item 2, and I will in fact, let me take the square root of both sides here. So taking the square roots here, we would get L sub I is less than or equal to square root AIBI times square root S sub Z. Okay, yes. Now let's go ahead and combine number 2 and this result here that we got. So let's call this result as number 5. So combine number 2 and number 5. So we would get L sub 1 is simply less than, so let's write that down. So S, which is equal to L sub 1 plus L sub n, is less than or equal to, we have square root A1 B1 square root SZ plus all the way to square root AN BN square root S sub Z, and we can factor out the square root S sub Z, square root A1 B1 plus all the way to square root AN BN times square root S sub Z. And finally, the expression inside the parentheses reminds us of the Cauchy-Schwarz inequality, and in fact, so this thing is simply equal to the product of, well, is less than or equal to, I should say, less than or equal to the product of the square roots of A1 plus all the way to AN, B1 plus all the way to BN, oops, no such thing here. Okay, and finally I can just go ahead and square both sides. So therefore S squared is less than or equal to, having squared these expressions, A1 plus up to A sub n times B1 plus up to B sub n times, we still have the square root of S sub Z, and finally, oh, we squared it, sorry. After having squared it, this is just an S sub Z here. S sub Z, like that. And finally, we have observed in step 3 that, oh, sorry for that, I forgot the absolute value terms. So we realize that this thing is nothing but S sub Y, and this thing is S sub X, giving us S sub X times S sub Y times S sub Z. Okay, so to recap, so the way we started is we laid down all the points of the set S on the 3-dimensional space, and we decided to classify those points in terms of their Z coordinates, and we assumed that the Z coordinates take n different values on the space. So we have layers starting from Z1 with a bunch of points on it, and so on. And then you have layer after layer of points, and we just focused on layer L sub I. We established that if the x coordinates of the points on layer L sub I, we have A sub I of those points, of those projections, and if the projections of layer L sub I onto the ZY axis accepts B sub I different values, the product, right, should be greater than or equal to L sub I, right? So that makes sense. And so on. In the second step, we realized that in the second observation, we realized that the sum of the points on each layer should be equal to S. That's obvious. The third observation was that the projections of the points onto the xz, yz, and xy planes are clearly defined in the problem. And all I did was to use this information related to layer Li to establish the appropriate formula for S sub x and S sub y in terms of A sub i's and B sub i's. And finally, in step 4, we just took a perpendicular projection, an orthogonal projection of the points on layer L sub I onto the xy plane. Now, all the points in the set S, the projections of all the points in the set S onto the xy plane was S sub z. Obviously, the projection of the points on layer L sub I onto the xy plane would have less elements, would be smaller. Finally, we combined these observations and also making use of the Cauchy-Schwarz inequality. Finally, we got the desired result that we were seeking from the beginning. So I hope you enjoyed this video and looking forward to see you guys in our next video.